Welcome to This Explainer. Today, we're diving into what is literally the ultimate cheat code of thermodynamics. We're looking at a mathematical framework drawn up way back in the 1870s, but here's the crazy part, it is still absolutely dictating the laws of cutting-edge material science today. It's called the Gibbs phase rule.
You know, the author Bill Bryson wasn't exaggerating even a little bit when he called it the Principia of thermodynamics. The French chemist Le Chatelier even put it on par with Lavoisier's foundational work. We're talking about Josiah Willard Gibbs's legendary 300-page paper published between 1875 and 1878. Basically, Gibbs invented a completely new visual and mathematical language to fundamentally define the symmetry of equilibrium. He took physical, chemical, and electrical phenomena and tied them all into one pristine, beautiful thermodynamic framework. So, here's our roadmap for this explainer. We'll start with the master equation, define the players involved, look at the proof of equilibrium, see how we adapt those rules, look at what happens when you break equilibrium, and finally we'll dive into the modern expansion of the rule. Let's get into it. Part 1. The thermodynamic law governing the universe, the master equation. This brilliantly simple equation right here is the master key. It calculates F, which is your degrees of freedom, based on C, your components, and P, your phases. Now, assuming standard pressure-volume expansion work, where N equals 1, we get the classic familiar form you've probably seen before, F equals C minus P plus 2. It looks like basic algebra, right? But the implications of this tiny little formula govern literally everything around us. Moving to Part 2, the three core variables of the phase rule, or as I like to think of it, defining our players. First up, we really need to nail down the definition of a phase. It is not just a broad category like solid, liquid, or gas. It's strictly about structural uniformity. Take water's solid state, ice. It isn't just one single phase. Depending on the temperature and pressure, ice actually has at least 15 distinct structural phases. Or think about solid iron. As you heat it between 912 and 1394 degrees Celsius, it changes entirely from a body-centered cubic structure to a face-centered cubic structure. It's the exact same state of matter, but a completely different phase. Next up, components. And it's super important to remember we aren't just counting basic elements here. A component is the absolute minimum number of chemically independent species you need to describe the system's composition. So if you have a water solution with 4 dissolved salts, technically, yeah, you've got 6 elemental species bouncing around in there, but because of strict chemical constraints, like the stoichiometry of the water molecules and the rigid requirement for electrical charge balance, you actually only possess 4 independent components. The universe naturally constrains itself, which is kind of mind-blowing when you think about it. And finally, we have the degree of freedom. Basically, this is how much you can mess with the system before you completely break the equilibrium. It's the maximum number of intensive variables, think temperature or pressure, that you can autonomously manipulate. So if you have pure water sitting there as a single liquid phase, you have a freedom of 2. You can tweak both the temperature and the pressure independently, and guess what? It stays water. But the second you boil it and steam appears, that freedom drops instantly. You can no longer change temperature without the pressure reacting if you want to keep both of those phases around. And it gets even more restrictive when you hit the exact triple point where ice, water, and steam all coexist perfectly together. Your freedom drops to exactly 0. You're left with an invariant state. If you touch the temperature or the pressure by even a fraction of a degree, one of those phases just vanishes. Let's move on to Part 3, the algebraic derivation of the Gibbs phase rule, and how Gibbs actually proved this equilibrium. This is where the sheer mathematical beauty of Gibbs's work really shines. Using the Gibbs-Duhem equation, he realized something profound. For a system to be perfectly stable, the chemical potential of every single component has to be completely equal across all phases. So if you take the total number of variables required to describe the system, which is P times C minus 1, plus the 2 global variables for temperature and pressure, and then you subtract the strict constraints enforced by those equal chemical potentials, which is C times P minus 1, the complex terms elegantly cancel each other out, and boom, you are left with our classic rule, F equals C minus P plus 2. It is pure deductive perfection. Okay, Part 4. Condensed systems and practical variations. Let's see how we adapt these rules for the real world. Say you're a metallurgist. You're working with solid and liquid metal alloys on a factory floor, which means you are generally operating under standard, unchanging atmospheric pressure. That pressure isn't fluctuating, and honestly, it doesn't meaningfully impact the solid or liquid phases anyway. So we just ignore the pressure variable entirely. Doing that drops the final constant in our equation from a 2 down to a 1, giving us what's known as the condensed phase rule. And this condensed rule perfectly maps an alloy's cooling journey. Picture starting with a hot two-component liquid mixture. It's one phase, so your freedom is 2. But as it cools down, crystals start forming. Now you've got a liquid and a solid, 2 phases. Your freedom drops to 1, meaning if you fix the temperature, the composition of the phases is totally locked. Finally, you hit the eutectic point. At this precise moment, the remaining liquid freezes simultaneously into 2 completely separate solid phases. That's 3 phases total. Your freedom is now 0. The whole thing freezes at one precise, unavoidable temperature and composition. Which brings us to part 5, external factors breaking perfect equilibrium. So the classic rule assumes we only really care about temperature, pressure, and composition. But what happens if you subject a system to intense magnetic or electric fields? Well, you instantly inject entirely new non-compositional variables into the mix. This completely warps the thermodynamic landscape. By adding these powerful fields, you increase the mathematical pathways to equilibrium. You are quite literally adding dimensions to the system's degrees of freedom. This dynamic brilliantly illustrates the clash between thermodynamic destiny and kinetic reality. The phase rule tells us what the ultimate, stable end state of a system should be. For instance, deep in the Earth, thermodynamics dictates that the mineral sillimanite should be the stable phase. Yet geologists constantly find kyanite, which is a metastable phase, instead. Why? Well, thermodynamics demands a change, sure, but kinetics determines how fast it actually happens. The atomic diffusion required to turn kyanite into sillimanite is practically infinitely slow at room temperature. So, the phase rule shows us the destination, but kinetics proves that matter can basically get stuck in traffic for millions of years. And finally, part 6, soft matter and the generalized phase rule. This is the modern expansion of Gibbs's work. Under Gibbs's classic, strictly enforced rules, a two-component mixture can mathematically only ever max out at 4 coexisting phases. If you hit F equals 0, you get P equals 4. That is supposed to be the absolute, unbreakable hard limit. But recently, researchers were blending rod-shaped and plate-shaped clay colloids and polymer gels, and they observed something that should have been impossible: 5 or even 6 distinct structural phases coexisting perfectly at the exact same time. It was a massive paradox that essentially violated the bedrock of physical chemistry. So, what gives? Well, the root of this thermodynamic paradox is a fascinating concept called polydispersity. Unlike atoms of oxygen or carbon, which are all completely identical clones of each other, microscopic colloids and polymers are inherently messy. They vary slightly in size, shape, and charge, and this continuous variation triggers chaotic fractionation. The larger particles literally push out the smaller ones, causing depletion forces that completely collapse the standard, uniform crystal structures that Gibbs originally based all his math on. To solve this massive paradox, scientists knew they couldn't just throw away Gibbs's work. They had to upgrade it. They developed what is known as the generalized phase rule by adding an entirely new variable, m. This m parameter accounts for all those complex microscopic interactions and size distributions. By adding m to the equation, the theoretical limit on phases suddenly expands, beautifully validating those crazy 5- and 6-phase systems we were seeing in the lab. This expansion reveals such a beautiful truth about our universe. Down in the nanometer realm, geometric shape, structural asymmetry, and size distribution aren't just trivial little details. They actually warp the Gibbs free energy curve just as powerfully as temperature or pressure do. They have literally been elevated to the status of fundamental thermodynamic intensive variables. Which leaves us with a really fascinating final thought to wrap up this explainer. We started with a rigid rule from the 1870s that perfectly predicted the behavior of water, steam, and steel. But now, we found that mere microscopic shape can bend those exact same fundamental equations of equilibrium. So it makes you wonder, what other invisible dimensions of matter are waiting out there right now, hidden deep into quantum or the cosmic scales, just ready to rewrite our rulebook of reality? Thanks for joining me to explore the architecture of the universe today.